Okay, so hopefully you guys did this. Can Calculus get you find assignments? And I just jotted down a couple of the answers because I want to get right into the lesson. But her average speed between Rock Falls and Maple Park was 68.75 miles per hour. It is possible that she was speeding because she could have gone more than 68 and then less than 68 and then it would average. But the police officers do not have convincing evidence that she was speeding there. All right, and then for 6, between Maple Park and Elmhurst, her average rate was 82.759 miles per hour. So, yes, they do have convincing evidence that she was speeding there because for her average to be speeding, she obviously was speeding. And there should be a moment that she was driving exactly that 82.59 or 759. So sometimes she was driving faster than that. Sometimes she was driving slower than that. But to get to that average, she was driving that at some point. All right. So today we're going to talk about the mean value theorem. And even though that seems kind of like a different type of way of thinking about speeding, it is actually related to the mean value theorem. So some important ideas is that if a function f is continuous on the interval from a to b, and this is a closed interval. I drew my first bracket a little rounded, but it needs to be a closed interval. And that same function is differentiable on the open interval from a to b. And then there exists a value c, where c is between a and b. So for a is less than c is less than b, such that f prime of c equals f of b minus f of a over b minus a. So let's talk about what that means. So f prime of c stands for the instantaneous rate of change. And this difference quotient stands for the average rate of change. So if a function meets these conditions, then there is going to be a point at which the average rate of change is equal to the instantaneous rate of change. So what that would look like on the graph I'm just going to draw a little graph. It's a continuous function. Doesn't look great. But we'll say this is A and this is B. All right. So if I wanted to draw something that represented the average rate of change, it would be the secant line between those. All right. So what this is saying, somewhere in between there is a tangent line. Oh, that's not me trying to get. There's a tangent line that has the exact same slope as the secant line. All right, so let's talk about how you prove it. And then the mean value theorem, we call it MVT. Almost said MVP. So how to prove with the mean value theorem? Number one, you have to check the conditions. So continuous on the closed interval, differentiable on the open interval. Second thing, we need to find the average rate of change. On the interval that you're given. And then we will make a conclusion. Using the mean value theorem. Okay, so we're going to do several examples. So the first thing we're going to do is we're going to use this function f as a twice differentiable function. And we know that f contains the 0.47 and the 0.74. So f of 4 equals 7 and f of 7 equals 4. We're going to show that there must be a value c on the interval from 4 to 7 such that f prime of c equals -1. So let's start with the conditions. If a function is twice differentiable, that means it's differentiable and it's also continuous. So we'll just make a little note of that. So since f is differentiable, and thus also continuous. Okay, so that's the first condition. We're good. Now we're going to find the average rate of change. I'm going to go over on the side to do that. We don't have a lot of room. So your average rate of change, we're going to do f of 7 minus f of 4 over 7 minus 4. Okay, so f of 7 is 4, f of 4 is 7, 7 minus 4 is 3. So we get -3 over 3, so that's -1. Now that's important. For this problem to work out, that does need to match up with what we're trying to prove, and it does. All right, so we're going to continue the statement. So since f is differentiable and thus also continuous, the mean value theorem guarantees that there must be a value c on our interval from 4 to 7. Oh, let me try that again. 4 is less than c is less than 7, such that f prime of c equals that average rate of change that we just found. So I'm going to rewrite it, which equals 1. Now I said c, but I wrote x, so let's be careful. Make sure if you're saying c here, you also and here that you also say it here. And it equals -1. All right, on example 2, it's a totally different type of question. So a test plane flies in a straight line with positive velocity v in miles per minute at time t, where v is a differentiable function of t. Selected values of v of t are shown in the table. So this gives the velocity in miles per minute at times in which the plane is flying. Based on the values in the table, What is the smallest number of instances at which the acceleration of the plane could equal 0 on the open interval from 0 to 40? All right, so this table gives the velocity, but this problem talks about acceleration. All right, but that's fine because if you guys remember, the derivative of velocity is the acceleration. So on the part of the mean value theorem, the f prime of c is talking about acceleration, right? Okay, so it tells you the function is differentiable, so that means it's also continuous. So let's start with that. So since v of t is differentiable and thus also continuous. All right. So we want to find points on this table at which the average rate of change of the velocity is 0. So that would mean that when you're subtracting, you get 0 in the numerator. So that would make the velocities equal. And it makes sense, hopefully, to you. The acceleration is 0, the velocity is staying the same. And so we have a situation here and here where both of those velocities are 0. So the plane's not accelerating in that interval, starts and stops at 7 miles per minute. All right, and then I do also notice right here, the plane is not accelerating between the 25th minute and the 30th minute, starts and stops at the same rate, and that looks like it. So we would say that the mean value theorem guarantees at least 2 instances where v prime of t or a of t is equal to 0, since there are 2 intervals and those intervals are from 0 to 15 and from 25 to 30, for which the average rate of change is 0. All right, let's look at number 3. So number 3, we have a graph that represents g of x. And so A asks us to find the average rate of change of g of x on the interval from -3 to 7. So we basically want to find the slope of that secant line right there. All right, so that's f of 7 minus f of -3 over 7 minus -3. Okay, so f of 7 is 1, f of -3 is -4. So that gives us 5 over 10, or 1/2. All right, for B, does the mean value theorem applied on that interval, but the closed interval, guarantee a value C such that G prime of C is equal to this average rate of change? So this function is continuous on that interval, but it's not differentiable at a couple of points. It's not differentiable anywhere where there is a sharp turn. So I would say no. The mean value theorem does not apply. Because g of x is not differentiable for all of that open interval from -3 to 7. There's 3 points where the function is not differentiable. Okay, we're going to do one more problem. It's kind of a long problem. So for 4, we're going to consider the function h of x, which is equal to 3 minus 5 over x. We have a graph pictured, and we want to know, does the mean value theorem apply on the interval from -1 to 5? Why or why not? Well, we can't really see what's going on underneath where y is -3, but because we're smart and we understand continuity and where there's going to be breaks in the graph, when x is 0, that function is not going to be defined, so it's not going to be continuous when x is 0. So we're going to say no. H of x is not continuous at x equals 0. So the mean value theorem is not applicable on the interval from, I wrote that in the wrong place. So the mean value theorem is not applicable on the interval from -1 to 5. All right, and then the second question asks, does the mean value theorem apply on the interval from 1 to 5? And it does, because the function is differentiable and continuous. So we would say yes here. H of x is continuous on 1 to 5 and differentiable on the open interval from 1 to 5. So the mean value theorem is applicable. Right, and then graphically, what does the mean value theorem guarantee for that interval? So this is kind of what we said like at the very beginning, that at some point the secant line and tangent line are parallel. Okay, so here is -1. You are going to 5. Sorry. I'm sorry. Here's +1. 1, 2, here. Okay, so here's my secant line. I'm going to graph it. It's really good. So there's some point somewhere that the tangent line is going to have the exact same slope. Oh, that's pretty good. So we can estimate it to a little bit more than 2 for the x value. All right, so the last part, we're going to apply the mean value theorem to find the value or values of c guaranteed for h of x on that interval. So we want to know what that value, what that point is right here, what this x value is. All right, so let's start off by finding the average rate of change. So it's going to be h of 5 minus h of 1 over 5 minus 1. Okay, and we can plug 5 in to our function, or we can guess looking at the graph. Let's just, either way, we're going to get 2 for h of 5. We're going to get negative 2 for h of 1. 5 minus 1 is 4. So that's going to give us an average rate of change of 1. Yep, I'm looking at that. That does look right. Okay, and then we're going to find the derivative of h of x. So I'm going to rewrite h of x a little bit so I can just use the power rule. So I'm going to write 5 over x is 5x to the negative 1. And then when I find the derivative of 3 is 0. The derivative of this I would multiply by negative 1 and take 1 away from negative 1. So h prime of x is going to be 5 over x squared. Okay, so we want to find a value for c that we can put where x is and have it equal 1. So what we want is for 5 over c squared to equal 1. The instantaneous rate of change equals the average rate of change. Right, and to solve this, I would multiply by c squared and then take the square root. Right, so I'm going to get that c is positive and negative square root of 5. But are those both? And we only have 1 point, so that negative square root of 5 is not in our interval. So it is just the square root of 5, not the negative square root. Right, and square root of 5 would fall about right there between 2 and 3, closer to 2. Now there is one on your assignment where you're going to need to use a calculator to solve for C. So just remember that you get if we were going to do this one in the calculator, if we have 5 over c squared equals 1, we would get everything on one side and then type it into y1 and then calculate a 0. So that's second trace. And then choose number 2, which is 0. All right, so your assignment is topic 5.1 worksheet.